BV-BFV Formalism.
Okay, so I will start with actually some background on the supermanifolds, actually graded manifolds, and then I will move on to BFV and BV and some generalization called BF and V, and then somehow to the main point, which is the Rax version, which are well, these structures, but with some failures. And we'll see that these is related actually to field theories on manifold with boundary. And then I will move on to quantization, and then I will discuss some examples, especially AKZ theories and the Poisson model. Okay, so let me just recall what graded manifold is. This is also called sometimes supermanifold. So this is like a manifold, but in addition to the usual commuting coordinates, we also have some odd coordinates. And the odd coordinates anti-commutes with other odd coordinates and commute with the even coordinates. So the correct mathematical definition is that we have actually a sheaf over topological space, and these are sheaf of rings. And the assumption is that locally these rings are isomorphic to infinite function on some open domain, tensor product, some exterior algebra. Okay, but actually it's easier to, or for the presentation to work with coordinates. I call it graded manifold and not super manifold because for basically all the application I'm going to discuss, it's better to have an additional degree in integers. This is what in physics is called the ghost number. And in principle, these are completely unrelated. So functions or coordinates have both a parity that is responsible for the commutativity and some degree. But for all the application I will discuss today, actually, I will assume that the parity is just this degree modulo 2. So I will basically talk only of a degree. So in particular, if M is a graded manifold, it's a full algebra function. So this will be the global sections of the sheaf will be a graded commutative algebra. And let me start with the first example for this. This is what we call the shifted tangent bundle. So M is just an ordinary manifold. Then we take its tangent bundle and we declare the coordinates of the fiber, that is the velocity coordinates, to be odd and of degree 1. So here, the base coordinate Q of degree 0, the fiber coordinates, maybe thought of as velocities, are odd and of degree 1. And so in particular, when you take functions, these are by definitions sections of the exterior algebra of the dual, so of the exterior algebra of the cotangent bundle, and so these are differential forms. Okay, so this is just a simple example. And the idea is to think of the algebra differential forms actually as the algebra of functions of some new object, which is a graded manifold. Now, a very important ingredient for what I'm going to discuss is the so-called cohomological vector field. So this is a vector field which is odd as degree 1 and commute with itself. So vector fields are defined, like in generalizing what happens on C-infinity manifolds, as derivations on the algebra of functions. And well, locally can also be expressed as linear combination of derivatives with coefficients given by functions, but probably it's better to have this global definition where vector fields are derivations on the algebra of functions. And now we'll focus on vector fields that are odd and commute with themselves, as it's written here, which is a non-trivial condition for odd vector field. Actually, this is an integrability condition for odd vector fields. And now the point is that, so a vector field is a derivation. So now I assume that this derivation is odd as degree 1, and actually this condition set is square to 0. So a cohomological vector field is the same as a differential on the algebra function. So this is why it's called a cohomological vector field. So let me give you two examples. So the first example is what I discussed already, the shifted tangent bundle. So we saw that the algebra function is given by differential forms, and on differential forms we have the de Rham differential. So since it's a derivation, it can be thought of as a vector field. So in particular, it's a cohomological vector field. And of course, in local coordinate, you can write it this way. It's a linear combination of the velocities times the derivative with respect to the corresponding coordinate. And the second example is the case of a Lie algebra. So suppose that we have a Lie algebra G, we shift it by 1. So its functions now are the exterior algebra of G dual, and on the exterior algebra of G dual, we have the Chevalier-Alembert differential, which is then a cohomological vector field. It can be written as following coordinates. So we choose some coordinates. Oh, what happened now? Become a moment. Okay. So so I introduce coordinates. Now coordinates are odd and at degree 1. Once I introduce coordinates, I can define the structure constant of the Lie algebra, and then in this representation, the Chevalier-Alembert differential can be written as this odd vector field, which is quadratic. So it's a linear combination of this bilinear term in the coordinates times the structure constants and derivative with respect to these coordinates. So this is what in physics is called the BRST operator, but it can be just defined this way in the supermanifold, and usual the algebraic language is a Chevalier-Alembert differential. Now, the next ingredient for my discussion is the notion of a graded symplectic form. So I'm calling usually, of course, you know, the symplectic form is a closed non-degenerate form. We can make sense of differential forms on graded manifolds. Simply we define one forms as dual of vector fields, and then we take the exterior, well, the graded exterior algebra generated by one forms. So these define differential forms. In particular, we focus on two forms, and we want them to be closed. So also the notion of the ramp differential can be generalized to supermanifolds. So we have the condition, express condition that the two form is closed, and we want it to be non-degenerate. And non-degeneracy is defined the same way. Well, for example, we can go to local coordinates, so then the two form is expressed by some matrix, and you want this matrix to be invertible. Or equivalently, you may say that once you have a two form, you can plug in vector fields, and this way you get one forms, and you want this map to be a bijection. Moreover, we have this internal degree. We have an internal degree because it's a graded manifold, and so we can also fix the degree of the differential form. So in particular, we will consider now symplectic form of some internal degree n. So this probably will become more clear in example. So now take the cotangent bundle shifted by 1. So on the cotangent bundle, we have a canonical symplectic form here, sum of the PDQ, where Q are the coordinates on the base and P are the coordinates on the fiber. But now I declare the fiber coordinate to be odd and of degree 1. So now these closed non-degenerate two form as degree 1, because the Q have degree 0 and the P have degree 1. Okay. Now, the functions on these graded manifolds are, by definition, sections of the exterior algebra of the dual of the cotangent bundle. That is, section of the exterior algebra of the tangent bundle, and these are multi-vector fields. So functions on this graded manifold are multi-vector fields. Now, we have this symplectic structure. We can compute the corresponding Poisson bracket by the usual procedure that is done on the usual symplectic manifold. And an easy check shows that this Poisson bracket on the supermanifold, when you graded manifold, if you interpret it, or if on this algebra, if you interpret it as the algebra of multivector fields, turns out to be this Houghton-Dye-Noyes bracket for multivector fields. And this example can be generalized to the shift by n, where n is some integer. And now, according to our convention, the parity is this degree modulo 2. So if n is odd, is precisely what you had before, but now vector field will have degree n, bivector field will have degree 2n, and so on. And if n is even, instead, well, we now consider functions on the cotangent bundle, so usual function of the cotangent bundle, and but now we have the notion of degree. So, for example, polynomial in the momenta of degree k will have degree k times n in this new grading. And the canonical symplectic form now will be a graded symplectic form of degree n, because Q still has degree 0, but P has degree n. Okay, now comes the crucial point is to put these two structures together in what some people call differential graded symplectic structure. So this consists of a graded manifold together with a symplectic form and the cohomological vector field that are compatible. So So here assume that omega is a graded symplectic form of some degree n, and Q is a cohomological vector field that is odd, degree 1, and Lie commute with itself. And the compatibility condition is that the Lie derivative of the symplectic form by the cohomological vector field is 0. And okay, there are several ways of defining the Lie derivatives in a supermanifold, like in the case of manifolds. And I mean, in principle, you can integrate the ordinary differential equation associated to this vector field, compute its flow, and then define the Lie derivative as a derivative of the pullback of the flow. But you can also prove, like in the case of manifolds, that you have a Cartan's magic formula. So actually, this Lie derivative can be written in a purely algebraic way as the commutator between the contraction and the Ram differential. So probably it's easier to work this way. Okay. Now, a stronger version, which is often useful, is to assume that Q is not only symplectic, but it's actually Hamiltonian. So namely, to assume that there is some function S with the property that the contraction of Q with the symplectic form is a differential of this function. Now, since I assumed omega to have degree n, and I assume, oh, maybe I can see, yeah, it is better, okay, yeah. Since I assume, oh, now this will become small again, okay. Okay, so since I assume omega to have degree n and Q to have a degree +1, this function S will have degree n +1. Okay, so and now I can rephrase the data by saying that I have a symplectic structure, a cohomological vector field, and some function S, such that the contraction of Q with omega is the differential of this function. Now, this condition that...
Excuse me, please. May I ask a little question? Your D, just little d, is degree 0, or you do not assign
yes,
the degree to it?
So yeah. So here actually, yes, I take the two degrees apart. So we have the internal degree n and the differential form degree. So we have 2 degrees. I take them separate. I don't take the total degree. Okay. So in this setting, D as degree 1 with respect to differential forms, but as degree 0 with respect to the internal, I mean, the graded manifold degree. Okay, so it transforms the functions into a 1 form, but it doesn't change the degree of the function. Is it clear?
It's clear, thank you.
Okay, now this condition that Q Lie commutes with itself is actually almost equivalent to the condition that S Poisson commutes with itself. So this is just the basic fact, symplectic geometry, that the Hamiltonian vector field of a Poisson bracket is a Lie bracket of Hamiltonian vector fields. So actually the correct statement is that the condition that Q Lie commutes with itself is equivalent to the condition that the Poisson bracket of S with itself is some constant, okay, because it has it should produce a 0 vector field. But now, by degree reason, you see that in most cases, this constant must be 0 because this Poisson bracket will be a function of a certain degree. And so unless this degree is 0, this function must be necessarily 0. Now, happens now. 1 second, I have to go back to full screen. Okay. Okay, another interesting thing is that this condition is actually not so strong. Actually, Di Marotem observed that unless n is equal to -1, this condition implies the existence of a Hamiltonian function. The reason is that on a graded manifold, you have the so-called graded Euler vector field. So this is defined this way. So if a function has degree f, you define E applied to f to be just a function multiplied by its degree. It's very easy to see that this is a derivation, so it's a vector field. And now what you can do, you can contract your symplectic form with the vector field Q and the vector field E. This will give you a function. And then you can easily check that if you take the differential of this function is n+1 times the contraction of omega with Q. So if n+1 is different from 0, you can divide by n+1 and produce this Hamiltonian function.
So sorry, Alberto, just a brief question. So does it mean that if n is not equal to -1, this means every odd vector field preserving omega is Hamiltonian?
I was assuming Q to have degree +1.
Yes.
So this is the one that appears here. Yes.
Yeah. So actually,
exactly.
it's always Hamiltonian. It's not an extra assumption.
Almost always. The point that, well, the case n equal -1 is important because this is the BV case.
It is the case?
The BV, Batalin-Vilkovisky case, is precisely the case n equal -1. So in that case, yeah, this is not guaranteed. And actually, that's why, in physics, when you do quantum field theory, you have to provide the Hamiltonian function. Mm-hmm. This is more information than just the cohomological vector field.
Okay.
Okay, so let me summarize the data here. Now I would assume omega to have degree n-1, so n will be the degree of the action, and q is fixed of degree 1. And then the fundamental relation between the three objects is this one that says that S is a Hamiltonian function for q. And okay, and now, yeah, this was the other comment, that q bracket q equal to 0 is equivalent to S Poisson bracket with S equal to 0. Now with this new n is different from -1, which I think in the previous notation would have meant n different to -2. Now here I want to present these two things because there are two different languages. So there is a language of differential graded symplectic structure of degree n, where n is usually taken to be the degree of the symplectic form. But now there is a BV language where it's better to take n to be the degree of the action S. And actually, I will call this a structure, instead of differential graded symplectic structure, a BFNV structure. So for example, for n equal to -1, for n equal to 0, which means action of degree 0, the F goes away, so this is the usual BV. And we'll see in a moment that another very important case is n equal 1. So this is a case where a symplectic form has degree 0, so this is how a generalization of used symplectic geometry. This is what is called BFV. So actually, let me just summarize it here, and then I will go more into details. So n equal to 0 is the usual Batalin-Vilkovisky formalism that we use to study gauge fixing in quantum field theory. The case n equal 1 is BFV. So this is a generalization of symplectic geometry because symplectic form now is degree 0, like in used symplectic geometry. And this is used to describe symplectic reduction in terms of a cohomological resolution. And I will explain this in a moment. Let me mention one more case. This is the case n equal 2. So here I assume that the symplectic structure is degree 1 and the action S is degree 2. And we already had an example of this sort. So when you consider the cotangent bundle shifted by 1, we saw that the canonical symplectic form had degree 1. And in this case, a function of degree 2 becomes a bivector field. And so the condition that this function Poisson commute with itself is a condition that this bivector field commute with itself using this Houghton noise bracket. So this is the same as a Poisson structure. So BF2V is almost the same as Poisson structure. Actually, it is exactly the same as Poisson structure if I make the assumption that I only have coordinates of degree 0 and of degree 1, as in the example I already discussed. In the general situation, when I also have coordinate of other degree, what you can check is that actually, well, a function of degree 2 will be some non-homogeneous linear combination of multi-vector fields of different degrees, but also of different internal degrees, so that the total degree is 2. And actually, they can be collected together by defining an L-infinity structure on the algebra function. So actually, this is what we should call a Poisson structure of homotopy or a Poisson infinity structure. So here's just the dictionary. BF2V is the same as Poisson infinity. Okay, now I will describe more in details the case n equal 1 and n equal 0. I mean, I already discussed the case n equal 2 in the important case when things are strict and not up to homotopy. So let me make a short digression on symplectic reduction. So let me start with a very simple example. Suppose that you have an ordinary manifold n with a symplectic form and some submanifold of codimension 1. suppose that this is actually given by some constraint phi. So there is some function phi, and C is a zero locus of phi, and I assume that it's a submanifold. So actually phi satisfies all the assumption of the implicit functional theorem. Now, as you know, that if you restrict now the symplectic form to C, it becomes degenerate, because well, C is odd dimensional now. But you can also easily see that the kernel of the restriction is precisely given by the Hamiltonian vector field of the constraint phi, is a span of the Hamiltonian vector field of phi. Well, first thing is that, well, if you contract omega by the Hamiltonian vector field phi, you get d phi, and by definition, phi vanishes on C, so d phi is also equal to 0 on C. But you can see that apart from multiples of this vector field, there is nothing more. So this is exactly the kernel. So what we want to do now, this symplectic reduction, is to take this submanifold C and mod it out by the distribution generated by this Hamiltonian vector field. And for simplicity, well, okay, the good situation is when the quotient is smooth. Now, what happens if the quotient is not smooth? Well, these are what often happens. So the idea is to deal with it algebraically. So the first guess is simply the following. Well, observe that, well, first suppose that the quotient is smooth. Then you can characterize functions on the quotients as function on C, which algebraically are function on n modulo the vanishing ideal of C, that is the ideal generated by phi. And then to go to the quotient, you take the subalgebra that is invariant under the action of this vector field. And the idea that now this is completely algebraic, so this makes sense also in the case when the quotient is not smooth. Now, there is an equivalent way of expressing this quotient. So instead of dividing by the ideal first and then taking the invariant part, you can take first the invariant part and then dividing by the ideal. But here you have to take, well, invariant up to the ideal. So this n phi is actually the Lie normalizer of the Lie subalgebra generated by phi. So this consists of all functions on the manifold whose Poisson bracket with phi is proportional to phi. Okay? And then when you mod out by phi, you get exactly the same as modding out by phi first and then taking the invariant part. And now the idea that this is the second description can be expressed homologically as follows. So what we do, we add two new coordinates, B and C, C as degree 1 and B as degree -1. We extend the symplectic structure by the canonical one, dB dC, and we take a function now of degree 1. So basically using the gradients we have, the only function of reasonable function of degree 1 we have is C, the coordinate C times the constraint phi. Then we can compute the cohomological vector field, and we easily see that Q applied to B is a momentum of C, produces exactly phi from here. If you apply Q to some function, you get exactly the Poisson bracket of this phi with a function times this vector C. And if you apply Q to C, you get 0 because this function does not depend on B. In particular, if we focus now on function of degree 0 and -1, we have these results. So this is the most general function of degree 0, either a function on n or a function on m times the coordinates C and B. And when you apply Q, you get a linear combination of these two terms. So you see that Q applied to this function is 0 if and only if phi bracket f is equal to g phi, which is precisely this condition. So the kernel of Q on function of degree 0 is precisely this Lie normalizer. On the other hand, this is the most general function of degree -1. It is a function n times the coordinate b. If you apply Q to this, you get this. And so in particular, you see that in the first component here, f, you just shift the function f by a multiple of phi. And so if you now mod out by the image of Q, it's the same as modding out by this ideal. So the result is that if you take the cohomology of Q in degree 0, you reproduce exactly this algebra here. And actually, something that is even nicer, that you made it this year, is that since this differential Q is a Hamiltonian vector field, this is compatible with the Poisson structure. So in particular, this cohomology will be a Poisson algebra, and you can check that actually this equality is actually an equality of Poisson algebras. So the idea is that now we have reconstructed the Poisson algebra of function on the quotient as a cohomology. And the idea is now that, well, instead of going to the quotient, instead of going, well, to this quotient here, you can just stay at the level of this complex and now work in the category of complexes. And this is a better description of the quotient. So this is called the cohomological solution.
Alberto, just a short question.
Yes?
So you show how the zeros homology looks like. What about, is there some nice example where you would have high homology?
Thinking if I make the correct assumption, thinking here in this example, if phi really satisfies the condition, the implicit function theorem, there should be no other homology. But in other example, there can be more homology. So I mean, a true resolution, yes, would be this result plus the condition that all the other homology groups vanish. And this is not always guaranteed. And actually, well, usually in application it's not true, but well, you just take it for that. I mean, just.
So you're saying the high homology would be related to the fact that that the level surface is not a manifold?
I think in this example of codimension 1, yes. But in a high codimension, I'm not sure. I think it's yeah, there can be some higher homology. And also some lower homology. Here you have, you see this complex has both terms in the positive and negative degrees.
I think there's also another question. Yes? Renat Kashaev, I think, wants to ask a question.
Yes.
Yes. So my question concerns the ambiguity in the choice of function phi. If you multiply it by some non-zero function, does it change something in the formalism?
Well, yeah, but it gives you something isomorphic.
And you have some explicit description of this isomorphic.
Yeah. Yes.
Okay. Thank you.
Important point that, yeah, this function should be different from zero everywhere.
Mm-hmm.
Now, the generalization of the previous slides in the case of a coisotropic submanifold, and for simplicity, let me describe it in the case where the coisotropic submanifold is defined by constraints. So here, and I assume that I have R functions, phi 1 up to phi R. I assume that they satisfy the assumption of the implicit function theorem. So there's zero locus, the common zero locus is a submanifold. And for this submanifold to be coisotropic, you have to assume that the Poisson brackets of this constraint vanish on the submanifold. This means that the Poisson brackets is a linear combinations of the constraints as well. So this is what in physics is called the first class constraints, and in symplectic geometry is called the coisotropic submanifold. Now again, you want to restrict the symplectic form to this coisotropic submanifold, will be the degenerate, but again, you will see that its kernel is generated by the Hamiltonian vector fields of the constraints. And so this is called the characteristic distribution. It's an involutive distribution, so it's integrable. And again, the good situation is when the quotient is moved, and this is called the reduced phase space. The cohomological resolution can be done along the ideas that I've described. So we'll give you the results. So this was actually what Batarin, Frake, and Ivikovsky did first, and then Stashev clarified. So the statement is the following. You can construct a graded manifold, which is the original symplectic manifold, and times some cotangent bundle, in such a way that the algebra function of the reduced phase space is the cohomology in degree 0 of the cohomological vector field. Now, this is constructed as follows. So what you do, you add R coordinate C of degree 1 and their momenta. So these are coordinates B of degree -1. You just extend the symplectic form by the canonical one. And then you take, well, more or less the same guess we had before. So now you take a linear combination of these C variables and the constraints. So this would be a function of degree 1. And the theorem says the following, that you can add something here, something in the higher powers of the B coordinate, in such a way that the Poisson bracket of S with itself is 0, and moreover, that the cohomology of Q in degree 0 is the Poisson algebra function of the reduced phase space. So I think Stashev gave somehow the full mathematical proof, and the result is actually not so difficult. It's just a nice application of homological perturbation theory. Okay, so but the point is that in principle, okay, if you algorithmically, if you want to apply homological perturbation theory, what you do is you just compute the missing terms here, order by order, in higher powers of B. The theorem tells you that you can always do it, but there are, of course, I mean, the procedure is a bit arbitrary. You have to choose at each order, and well, this could be a very long polynomial. I mean, the finite dimensional case, of course, it stops because the B are odd variables, but in principle, you can have a lot of corrections. There is a nice situation where you stop at the first correction. This is the case where the constraints phi I are the components of an equivariant momentum map. So in this case, you can actually find a solution that stops at the linear term in B. And the coefficients are the structural functions of this Lie algebra. So this is what is called the BRS or BRST formalism. And in this setting has been studied in detail by Poisson and Sternberg, together with its quantization. Okay, so this was what I want to say about BFV. And now let me make a short digression on BV. So this is this formalism that is used to discuss gauge fixing for quantum field theory, has been introduced by Batalin and Dilkovitsky. And now, well, I will give some modern presentation of it based on ideas that have been developed over the years by Witten, Schwartz, Khudaverdian, Shevera, and other people. So let me summarize the thing. So the idea is to take a not symplectic manifold. So for simplicity now, I will consider the symplectic manifold to be finite dimensional, which is not the case of quantum field theory, but it's the case where the following statements are rigorous. So suppose that F is a not symplectic manifold. So the first observation is that you can take half densities. So well, what are half densities? So densities are the things that you can integrate. So these are the things that somehow locally are functions, but when you move from one chart to the other, they transform with the Berezinian of the Jacobian matrix of the transformation. So these are the objects that you can integrate. Half densities are objects that transform with the square root of the Berezinian. And one nice result is that if your F is symplectic, you can have a notion of Lagrangian submanifolds. And if you restrict the half densities on Lagrangian submanifolds, you get densities there. And so you can integrate them. So the idea is that half densities on the whole symplectic manifolds are the natural thing to integrate on Lagrangian submanifolds. The second observations by Khudaverdian is that there is a canonical second order differential operator delta, the square to 0, which is defined on half densities. And this delta has important properties. So the first property is that if you integrate a delta exact half densities on a Lagrangian submanifold, you get 0, well, assuming that this function is integrable. And the second property is that if you have a delta closed half densities and the family of Lagrangian submanifold, parameterized, say, by some parameter t, the integral does not depend on the representative of in this family. So I will not prove this, just believe this. And let me just give you an example. So the example is when we take this odd symplectic manifold to be the odd cotangent bundle of some ordinary manifold M. In this case, one can prove that half densities on this odd symplectic manifold are the same as differential forms on the manifold. And in particular, among the Lagrangian submanifold of F, you have the odd conormal bundle of submanifolds of M. And it turns out that so here on the left-hand side, rho is interpreted as half density on F, on the right-hand side is interpreted on the differential form of M, and then you have this equality. If you integrate the half density rho on the odd conormal bundle of C, you get the same as integrating the corresponding differential form rho on the coisotropic submanifold C. And in this example, this delta operator, this is called the BV Laplacian, corresponds to the RAM differential and differential forms. And so in particular, 3 and 4 in these examples are related to Stokes theorem. Now, why is this important for field theory? So the idea is the following. In field theory, typically, you try to reformulate your field theory as having a not-symplectic manifold F, which somehow the manifold of fields plus some extra guys. And you have some reference Lagrangian, some manifold L0, which corresponds to, well, your understanding of the theory. But it turns out that the integral over L0 is ill-defined. And then the idea is that you deform this L0 by some LT, actually by some family of LT, which is defined for T in the neighborhood of 0, with the property that the integral over LT is well-defined. Now, if what you're integrating, so your Farad density sigma is delta close, then it doesn't matter which LT you choose here. And so you can take this as a prescription to define your ill-defined original integral over L0. Okay? So this is the gauge fixing procedure in BV. So it's actually better to express this in terms of functions. So to do this, you fix some half density rho, which is killed by this BV Laplacian, and then you can transfer this BV Laplacian to function. Namely, if you have a function, you can multiply it by this referent half density rho, you get a half density, you can apply delta, and then you get a new half density, and then you can divide by rho, because I assume that this half density is non-degenerate. And so you get back a function. So this defines delta applied to the function. And this delta applied to function as a second order differential operator with certain interesting properties. So in particular, if you apply it to an exponential, this is a typical situation you have in field theory. So assuming that this f is exponential of IH bar s, then the condition that delta f is equal to 0 is equivalent to this condition here, where this round bracket is a Poisson bracket associated with symplectic form, and this delta is the same delta as before. So this is called the quantum master equation, and is related to the equation we had before, that is that S Poisson commute with itself if this term is not there. And there are this situation where you can ignore this term. One situation is when delta S is equal to 0, which sometimes happens, and another situation when you work the classical level, that is you send this H bar to 0. So this was just some sort of digression to tell you how this classical master equation arises in this BV formalism. Now, the main point is that the quantum master equation makes sense in the finite dimensional case only, because you need the notion of these half densities on this BV Laplacian. But this classical master equation, which is just a Poisson bracket, can often be extended also to infinite dimensional case. So the idea when you want to study some field theory in the BV formalism is first to focus on the classical master equation, which usually well defined, and postpone the study of the quantum master equation to when you really start quantizing. Because at that point, you will have to regularize the theory anyway, and this regularization, well, if it's a good regularization, will give you also a compatible definition of this delta. Now, in this description of BV, I didn't use the Z grading. Now, the Z grading can be reintroduced. Now, the idea that we want this, in the case of BV, we want this action function to have degree 0, because degree 0 are the physical object in this language. And so this forces omega to have degree -1. And so this is why BV corresponds to the case where the symplectic structure has degree -1 and the action, or the Hamiltonian function S has degree 0. Okay. And so this is just this slide just to show you this. I mean, if you know a little bit of physics, this is a typical example when, well, BRST is a particular case of BV, but I will not discuss this. Okay, so should we make the break now, or because I'm now about to start with a new topic?
Sure, that's one of the possibilities for a break. Absolutely, if you think it's a good idea. So
this is a good point. Otherwise, I could go on like 2-3 more minutes.
No, it's like 2-3 more minutes is also possible.
Okay, so maybe we'll finish with this. Okay, so now this is the interesting situation. Assume that now we have the same data for a BFNV structure, but something does not work. So suppose that we have a gradient manifold M. We have our cohomological vector field Q. But now we have a closed to form of degree n-1. I drop the condition that should be non-degenerate, because it turns out that this is not relevant. And we have some function S of degree n. but I no longer assume S to be the Hamiltonian function of Q. Okay, so I can introduce this error term, alpha check, which is not necessarily 0. Now, as you see here, alpha check will be a function of degree n, the same degree as S, will be a 1 form, and it will be, of degree n. What you can do now, you can take the differential, these alpha checks. Now this will be a 2 form of degree n, which I will call omega check. And using Cartan magic formula, you will see that this omega check can also be written as minus the Lie derivative omega with respect to Q. So if omega is not Q invariant, this omega check will not be 0. Okay. However, this omega check now has better property. Well, first of all, it's clearly closed because it's exact. But now it turns out to be also Q invariant, because if you apply LQ to omega check, you have to apply LQ here. But since Q is odd, this LQ is an odd operator, so applying LQ twice is like applying 1/2 of the commutator of LQ with LQ, which is the same as the Lie derivative with respect to Q bracket Q. And since we assume the Q is cohomological, this will be 0. So the original omega was not Q invariant, but the new omega check is Q invariant. The problem that typically it is degenerate, but now, okay, let's do symplectic reduction. I assume that the quotient of M by the kernel of omega check is smooth. I will denote it by M underlined. And now on M underlined, we induced a symplectic form omega underlined, which is this omega check on the quotient. So this will be now closed and non-degenerate, end of degree n. And moreover, it's very easy to check that since, omega check is Q invariant, this Q is projectable, so it gives rise to a cohomological vector field Q underline on M underline. And you can also see that, by this assumption on degree, there is a Hamiltonian function S underline. So the result is the following, that now we have a BFN plus 1V structure on M underline. We have this symplectic form of degree n, this cohomological vector field Q underline, and this Hamiltonian function S underline. So let me repeat. So we start with the data of a BF and V manifold, but I drop the assumption that S is a Hamiltonian function of Q, and using them, we can construct a BFN plus 1V manifold, so 1 degree higher. So this can be seen the procedure to generate BFNV manifold out of weaker data. And maybe let me just comment a moment here that if you assume that not only that the symplectic form, the 2 form descends, but also its potential alpha check descends, then also on the quotient we can write omega underlined and some d alpha underlined. And now we can rewrite this equation by saying that the contraction of QV omega is equal to the differential of S plus the pullback. So this pi is a projection from M to M underline of this 1 form alpha underline. So this is what we call the modified classical master equation because of this error term. And now let me finish with an application. So as I said, this can be seen as a procedure to generate BFNV manifold, but this procedure actually appears in field theory as follows. So suppose that M now is a space of fields of some field theory on some closed manifold sigma. And let me assume, like in field theory, that all the data are local. So M is actually a space of jets of fields. And I assume that omega, Q, and S are integral over M of jets of the fields. Now, since omega, Q, and S are defined as integrals, now we can extend their definition also to the case when the source manifold sigma has a boundary. But now, if S contains derivatives of the fields, it turns out that something might go wrong. In particular, it may turn out that S is no longer the Hamiltonian function for Q. But now we can apply the construction of the previous slide, and now we produce a BFN plus 1V structure on the quotient. And it turns out that this quotient M underlined is related to fields on the boundary. And one reason is that in the bulk, IQ omega is equal to ds. So in the bulk, this alpha check is equal to 0, omega check is equal to 0. So in particular, the kernel of omega check contains translations, changes, deformations of the fields in the bulk. So in particular, we mod out by whatever happens in the bulk, and we only see what happens on the boundary. So the final claim is that this BFM structure is a structure on fields on the boundary, which by this I mean some jets of the fields on the boundary, including some transversal jets. And I think, yeah, this is a good point to make a break.
Okay, very good. Thanks a lot. Are there any questions or comments before the break? Any questions or comments? I recall you that to ask a question, you probably need to unmute yourself. Rare?
I have a question. How do I unmute myself?
A simple little question.
Rare and Chen Chang?
You were talking about this delta operator. You call it a Laplacian, which is of order 2. But you also had an example where that Laplacian was equal to the de Rham operator, which is of order 1. So
yes.
Can you explain that?
Yes. So, well, I was using this isomorphism between half densities on this special all-symplectic manifold and differential forms on the base. So when you apply these isomorphisms, this second-order differential operator becomes a first-order differential operator on the other side.
I see. Thank you very much.
Second-order differential operator on half densities, but when you're interpreted as an operator on differential forms on the base, it becomes first-order.
I see. I get it. Thank you.
The point that this isomorphism is not an algebra isomorphism. It does not preserve the wedge product.
Very good.
Okay. Chen Chang?
Oh, okay. So I have a question like this in certain slides, I am confused about this n, BFM, the number of n. So certain slides, this n is also the degree of omega, right? So
when I say BFNV, n is a degree of S.
N is the degree of S?
Yes. So the degree of omega is n-1.
Degree of omega, yeah, okay. Degree, but it's the same n. So degree of omega has to be n-1.
Yes.
And degree of S is n. And then on the in this case, one can construct this CF and NV.
So here, I start with S of degree n, but the new S here, S underlined, will have degree n+1. So I increase the degree.
When you go through this BF and V thing, and you do this reduction, right? So what I'm familiar with is the Poisson sigma model, right? Yes. So in the case of Poisson sigma model, n equal to what, 1? Or?
No. So in the bulk, n is always equal to 0. In the bulk of a field theory, in the BV formalism, n is equal to 0, always.
Okay, so let's say we do a Poisson sigma model on a square,
yes,
a two-dimensional square.
Yes.
Then in the bulk, n equal to 0.
Yes, and on the boundary, n is equal to 1.
Say it again.
And then on the boundary, n is equal to 1. And in this example of a square, actually, you also have corners, and actually you can go one step further, and on the corner we have something of degree 2.
And also in your description of BFV, you just described this, but in the Poisson sigma model, was it like, was this procedure you, well, I learned there was a question. So you restrict this whole thing on the way you do it is you separate the variable t and the variable spatial variable and t. Then you
sorry, my apologies. Do I understand correctly that in the second part we will have more information on the Poisson sigma?
A bit, yeah, a bit. Probably not. This Chen Chang question is more technical, so probably better to discuss it separately.
Maybe we can discuss it privately.
In private or at the end. Yeah.
Okay.
Yeah.
Thank you. So then I suggest to make a break and to resume at 4:10.
Okay. Maybe let me start from here. Actually, from this question was good. So yeah, in principle, this is a machinery to produce BF and V manifold out of weaker data. We saw this example in field theory. And actually the idea that in field theory, you start from BF and V structure for some n, assume that everything is local, and then you apply this machinery by taking some source manifold that has a boundary, and then assuming that this underlined is smooth, you get a BFN plus 1V structure associated to the boundary. Now, if you're lucky, this new structure is also local. And so in particular, you now can apply to the case of a boundary that has itself a boundary. And then you will produce a BFN plus 2V structure on its boundary. And in principle, you can keep continuing. There are some situations where you keep going on up to the case where you end up with something dimension 0. Other cases where you have to stop, either because this quotient becomes singular, or because things become trivial. So at some point it might happen that, I mean, this quotient becomes a point. So basically, I mean, there is no structure left. Okay, so this was the general thing. Now let me describe an application. So suppose that, yeah. So first let me discuss the application in n equals 0. So suppose that you start with a BV structure. So this is a case in n equal to 0 in the bulk in field theory. And then on the boundary, you get a BFV structure. So we saw that BFV corresponds to a cohomological resolution of symplectic reduction. And this is actually the symplectic reduction associated to what in physics is called the reduced phase space, which is the correct phase space for the theory. So for example, if you apply this, say, to electrodynamics in the bulk, what you get on the boundary is a cohomological resolution of the space of boundary fields where you impose, which are actually the electric field and the vector potential, where you impose the condition that the divergence of the electric field should be 0. This is Gauss' law, and you mod out by the corresponding Hamiltonian vector field, which are actually the gauge transformation. So this is somehow what happens when you go from n equals 0 to n equal 1. Now let me describe the case when you go from n equal 1 to n equal 2. So suppose that we have a field theory in n equal 1. So that means that in the bulk, we are giving this a cohomological resolution of a symplectic reduction. And now when we go to assume that this sigma is a boundary, on the boundary we get a BFL2V structure. So we saw that BFL2V means Poisson structure, possibly up to homotopy. And well, this is supposed to describe the current algebra or some generalization of the notion of current algebra of the theory. I will describe a simple example in the next slide. So, and a nice thing is that this construction is often compatible with cutting and gluing your manifolds. So cutting means that cutting glue means that you start with a manifold, you cut it along a submanifold dimension 1, you produce manifold with boundary, and then you try to glue them back together. And under some regularity assumption, this procedure is compatible with this construction is compatible with this procedure. And moreover, it's often possible to quantize these structures, and I will explain this later. Okay, so let me give you this example where we start in n equal 1, so cohomological resolution of a symplectic reduction, and we go to the boundary and we get a Poisson structure. So this is actually an example that should be familiar for everybody. This is a Chern-Simons theory. But we do it somehow on the boundary of the field theory. So we have a two manifold now. So the idea that we have the ingredient are a two manifold and the quadratically algebra, and you consider the space of connections on these two manifolds. So for simplicity of notation here, I will assume, well, my connection, well, my principal will be trivial. So my fields will be Lie algebra valued one forms on sigma. We have the Atiyah-Bott symplectic structure on sigma. And then we have a coisotropic submanifold given by flat connections. And it turns out that the reduced space is the quotient of the space of flat connection by gauge transformations. Now, if you want to do this in BV-BFV language that I described in the previous hour, this is an example where you actually have an equivariant momentum map. The curvature is actually an equivariant momentum map. So we have this Hamiltonian function S of degree 1 that stops at this term here, would be linear. So the first term, CF, is the one that imposes the constraints f equal to 0, and the second term VCC is the one that remembers for you the Lie algebra structure.
Alberto?
Yes?
I have a somewhat stupid question.
Mm-hmm.
I always get confused when you start calling those things an action, right? Whatever, because you always denote them as.
Yes.
And call them an action, even though this guy to me looks more like a BRST charge or something.
Yes, yes, yes.
So is it like kind of, are there some conceptually nice names of all those consecutive?
Sometimes it's called the BFV action.
Mm-hmm.
So, or the boundary action, or
yeah.
the reason why you call it action is because formally you always have this equation IQ omega equal to the S.
No, but of course, once you denote it as, of course, you call it action.
Yes.
So that's
no, but it's always somehow the Hamiltonian function for Q. That's the point. Okay. And the point is that sometimes, I will not explain this, but sometimes this BFV action becomes an actual action for a boundary theory. Like it's related, for example, in Chern-Simons, it's related to Westermino-Witten. I mean, you have to work more about it, but somehow this gives rise to Westermino-Witten action, for example. So there are good conceptual reasons to call it action anyway.
But you don't plug this thing on the nose into the path integral, so it's not action in the usual sense for sure.
Yeah. I will try to call it the Hamiltonian function, not the action. Okay, so this is it. Yeah, this Hamiltonian function for the symplectic reduction of Chern-Simons theory. And so here the space of fields is a space of connection times this cotangent bundle. The C variables are the variables of degree 1. So these are zero forms taking values in the Lie algebra. So this is called the ghost, and the B are called the anti-ghost. And now, if sigma has a boundary, it turns out that when you take the derivative of S, you have to integrate by part, because here we'll have some of the variation of A. So we get a term covariant derivative variation of A. And to produce a correct DAC term, which is the gauge transformations, you have to integrate by parts. And so there will be some boundary term, which is C delta A. And this will be responsible for the alpha check. And so omega check will be actually, well, delta C delta A, or delta A delta C. And it's actually, basically, this omega underline turns out to be this. And the idea that in the quotient, you basically ignore all the transversal jets of the fields. So the space associated to the boundary now, which is one-dimensional, is the space of connection A and the generator of gauge transformation C that have Gauss number 1, and that's it. Then you have the Q here, and you can check that, explicitly check that this omega is Q invariant, and it has this Hamiltonian function here. So this C DAC. Now, as I told you, in case of BF2V structure, where your coordinates only degrees 0 and 1, this should be a Poisson structure, and it actually is. So here you should think of the C variables that have the degree 1 as somehow the derivatives with respect to A. So this is actually a description of a Poisson by vector field on the space of connections on the circle, for example. And so since this Poisson structure contains a constant term, just CDC, and the linear term CAC, it's a Poisson structure associated to the dual of central extension of a Lie algebra. And actually, if you explicitly do this, you see that, well, the Lie algebra corresponding to this Lie bracket is just the Lie algebra of zero forms taking values in G with a pointwise bracket plus the usual central extension. So somehow this idea that this universal procedure produces for you the Kac-Moody algebra associated to Chern-Simons theory. So this is a very simple example, but the idea that you can apply this to every field theory and get somehow the corresponding Poisson structure in codimension 2, which somehow describes the current algebra. And for example, some ongoing project we have is for four-dimensional gravity, where, well, this exercise turns out to be quite complicated, but produces some interesting results. Okay, so maybe here I will skip these slides since we don't have much time. So the idea is that, actually, because I will go more in detail here. So let me skip here. Okay, so let me now start discussing quantization. So suppose now that we are in the bulk with the BV structure. So S is degree 0, and it's a usual action. And then we have some boundary structure. So now we'll use this notation for this, the BV space with, well, relaxed data. I will use the notation F, because these are the fields of the theory. And for this reduction, we use notation F boundary, because these are fields associated with the boundary. And on F boundary, we have a BFV structure. Now, the idea is that since the BFV structure in particular has a symplectic form, its quantization should be done by geometric quantization. The idea that you should produce some Hilbert space or pre-Hilbert space associated to this symplectic structure, and then you should quantize this function. So this function should be quantized to some operator, and the idea that, well, you would like this operator to have good properties. So since S bracket commutes with itself, this operator omega will commute with itself up to higher order in H bar, and the good situation where it's actually exactly commutes with itself. And the idea is that in the bulk, you do the functional integral with some gauge fixing, and the result should give you some vector in the pre-Hilbert space, and hopefully this vector is killed by this omega operator. And we will see a concrete procedure to produce this that works in several examples. And the good result, good outcome, is that our procedure has also nicer properties, namely is compatible with cutting and gluing. So the idea is that if you cut your bulk manifold into along a codimension 1 submanifold D, so then you apply this procedure on the manifold with boundary sigma 1 and sigma 2. This procedure will produce some vectors in the Hilbert space, one vector associated to sigma 1 and one vector associated to sigma 2. And what you can prove that if you pair this vector, you produce a partition function for sigma under some assumption. Okay. And what is interesting is that typically you don't want to integrate out all the fields. You want to do some sort of Wilson renormalization or to retain some data about well, so-called zero modes, which is a classical space, modular space of classical solutions. And this can be taken into account. I will explain this more in details. Now, the main assumption I will make is that this boundary symplectic form is exact. Otherwise, things becomes a bit more, well, actually quite more complicated. But actually, this assumption is not so strict. The reason is that typically when you start doing perturbation theory around some solution, we only look at the tangent space. And so basically everything is now formulated on affine spaces. So the two form is necessarily exact. Okay, so the idea now we are on the boundary. We have this exact BFV structure on the boundary, and we want to do geometric quantization, so we need some polarization. And I will consider the case of real polarization here. We'll start studying the case of complex polarization, but for this talk I will only consider real polarization. So a real polarization on a symplectic manifold is just an involutive distribution of vector fields with the property that at each point the distribution is Lagrangian subspace of the tangent space. And moreover, for simplicity, I will assume that the restriction of one form is 0 to the leaves of the distribution. Notice that, well, this one form may be changed. This is a, I mean, what matters is the two form, and you can try to adapt it to the distribution. And well, it's not always possible, but I assume that this is the case. And moreover, I will assume that the quotient of this symplectic space by this polarization is also smooth, and I will denote it by B. So this is the base space. So for example, if you have the usual cotangent bundle with the P and the Q variables, and you take the polarization to be the polarization in the P direction, this quotient will be the space of the Q direction, and the Hilbert space will be the usual function of the Q variables. Okay, and these are some of the image you have to have in mind. Now, we know that the whole space of fields, bulk fields, projects to the space of boundary fields just by restriction to the boundary, and the space of boundary field projects to this base field. And what I assume now is that this projection splits. So I assume that I can write the space of bulk fields as a product, as Cartesian product of the base of this polarization and the rest. So this Y will contain bulk fields, but also the leaves of this polarization. This is not, again, a very strong assumption because, as I said, typically we will work on affine spaces. But what is strong is that we want this splitting to be compatible with the two form in the bulk. And the compatibility is that essentially this B for the two forms should be just a space of parameters. So omega should be a symplectic form on Y depending parametrically on B. Okay, so in particular, the differential form will not have differential of the base, contain differential of the base coordinate B here. So this is a very strong assumption. And we will see that these are some consequences that are very, very strong. So this is something, well, that you have to assume. And when you are dealing with some field theory, you have to check that this is possible. Okay. And I assume omega to be non-degenerate on Y. Now, remember that we have this modified classical master equation. Let me see if I can write now. No. No. Oh, for some reason I cannot write. Why? Ah, okay. Yes. So remember that we have this equation IQ. No. Okay. Oh, I have to write with this. So IQ omega was delta S plus the pullback of alpha boundary. Okay, so this was our equation. So let me go back to Spotlight. Okay, and now under these assumptions, I can write it this way. I take the vertical part of delta S and the horizontal part of delta S. Now, if I take the vertical part of delta S, I see the term IQ omega, where I only see the Y part of Q. But I don't see alpha boundary because I assumed that alpha is adapted with the polarization. So, so alpha vanishes in this vertical direction. So the vertical part, I only see Q, but I don't see omega. And in the base part, I don't see Q because, as I said, omega is only parameterized by B, but doesn't have components along B. So this term disappears, and I only see alpha boundary. So I will no longer write pi star here. Okay, so now this modified classical master equation splits into these two separate equations. Now, a simple computation using just Cartan calculus shows that we can compute the Poisson bracket in the Y direction. Remember that now I assume Y to be non-degenerate. And now since delta YS is exactly equal to QI omega, so now S is really the Hamiltonian function for the vector field Q, I can compute the bracket. And it's the same as contracting omega twice with Q up to this factor 1/2. And the interesting thing is that the result of this computation turns out to be the boundary action, S boundary. So this is the Hamiltonian function degree +1 for the BFV boundary formalism. Okay. So as you see, the classical master equation is no longer satisfies. It has an error, but this error is something that we know. Now, let me make the first assumption that we have adapted Darboux coordinates on this boundary BFV space. Namely, adapted means that the one form alpha is the sum of a P delta B. So B are the coordinates on the base, P are the coordinates on the leaves, and I assume that the one form is written this way as a sum of P delta B. Then the second equation is very, very simple. It just says that the derivative of S with respect to some B coordinates is the corresponding P coordinate. So this in particular means that S, so this is the usual action, the bulk action, is linear in these B variables. In these P variables. In the B variables. Is linear in the B variable. And you see that this is a very strong condition. Okay, now let's focus on the first equation. So let me assume that S is killed by delta Y. So I assume that well, this simplifies a little bit the quantum master equation. So under this assumption, when apply delta Y to the exponential of bulk action by the property of delta, which is a second order operator, I will get a term which is S bracket S. And in principle, I should have this other term delta S, but I assume it to be 0. But now the crucial point is that we show here that S bracket S is this S boundary. So I can rewrite up to this factor H bar. You can see that delta, the BV operator applied to the exponential of the bulk action, is just the exponential of the bulk action multiplied by the boundary action. Okay, so this is some cute equation. Now let's move to the other equation. So remember that we had that, maybe do here. So remember that we saw that delta S, delta B was equal to P. Okay, so when we do the quantization, so if you do the Schrödinger quantization, right, we see that, well, derivative with respect to the base coordinate is up to IH bar, the quantization of the momentum operator. So we can rewrite this equation by saying that the quantization of P, that I will denote by P hat, applied to the bulk action is minus IH bar P. So here, not to make confusion, this P hat is a quantization of P as an operator, essentially is the derivative with respect to B, whereas this P with respect to the Hilbert space is just a parameter. So this is a variable P in the space Y that contains also the bulk field. Okay, so but we have this equation. And now look at what happens. So if you take now the bulk action and we quantize it by Schrödinger prescription, namely we replace every occurrence of P by this operator and we put all these derivatives to the right. So this is a usual the usual ordering for differential operators. Then when you apply this omega to the exponential of the bulk action, you obtain just the exponential of bulk action multiplied by S boundary. So what is crucial here is that the bulk action is linear in the B variables. Okay, so this is crucial for this equation. Okay, but now let's summarize. We saw that applying omega produces S boundary, but we saw before that applying delta also produces S boundary. So we can get rid of S boundary just by putting the two operators together. So what we see here is that the exponential of the bulk action is necessarily killed by this operator, H bar square, BV operator along the fiber, plus this operator omega acting on the pre-Hilbert space. And this is called the modified quantum master equation. I think there was one example where this equation was found before our general treatment. This was a paper by Anton and Pavel Nyov on the one-dimensional Chern-Simons theory, but now we see that this equation is actually general. Okay, now probably want to get rid of these things. Okay. Now, let me remark what I said that I make this assumption that delta S is equal to 0. This is not really necessary. If it's not the case, basically you can do exactly the same, but instead of taking the boundary action, you have to get the boundary action with some corrections. And so this in particular tells you that this omega will no longer be the Schrödinger quantization of S boundary, but the Schrödinger quantization of this new function that has H bar correction, which you can also think of as a different quantization of S boundary. But anyway, what is crucial now is this equation. Now you can forget the whole procedure and just focus on this equation. Now, so this is the operator that appears in this equation. And now we know that delta squares to 0. We know that delta commutes with omega because delta acts on the space Y and omega acts on functions on the space B. So this means that if you want this omega, which is a quantization of S boundary, to square to 0, so remember that classically we know that S boundary commutes with itself, so it would be nice to say that also this omega squares to 0. Well, we see that this is equivalent to the condition that this omega squares to 0. And this is an assumption I'm going to make now because I want to consider this omega now as a co-boundary operator on the pre-Hilbert space. So the idea is that, remember, classically we wanted to consider the cohomology of Q. The cohomology of Q in degree 0 gave the Poisson algebra function in the reduced space. Now I want to take the cohomology in degree 0 of omega y and interpret this as the pre-Hilbert space quantizing the reduced phase space. But for this, I have to assume this to be a co-boundary operator, which means I have to assume this omega to square to 0. So if this is not possible, this is a signal of anomalies for the theory. Okay, so now let's assume the modified quantum master equation here. So this omega y is this combination of operators. And suppose that the space y of bulk fields splits in the product of y prime and y double prime. We should think here some sort of Wilson normalization. The y prime are low energy modes and the y double prime are high energy modes. And the idea is now that we do the BV procedure, but only for y double prime. That is, we choose a Lagrangian submanifold y double prime, and we integrate the exponential of the action there. So the result will be a function of b, so it is an element of the pre-Hilbert space H, and tensor a function on y prime. And one can show that this integration is compatible with this operator, namely, this psi will be killed by the omega operator for y prime. And moreover, you can show that if you change this gauge Fission L, this psi changes by an omega prime exact term, which means that these push forward procedures is compatible with this coboundary operator. So what matters actually the cohomology of omega. And so this is somehow the BV version of Wilson renormalization. So these appeared in some, I think this was first suggested by Losev. It appeared in Pavlov thesis, and it's also the basis of Kevin Costello program for BV. And okay, in particular, if y prime is just a point, so if you integrate everything out, you just get some element of H, which is killed by omega and is defined up to omega exact term. So you have to go to the cohomology, and the cohomology is a physical state. So this procedure is a way to produce physical state out of the functional integral in the bulk. Okay, so here is just a summary of the theories where we have applied this formalism. Actually, essentially, well, the basic case is so-called abelian BF theories. So these are theories where the action, maybe right here. So these are theory where the action is something like integral of B d A, where typically, well, A and B are differential forms, and D is a de Rham differential. And we show that in these examples, the whole procedure works. There are no anomalies, everything works. And then we studied several deformations of the theories. So for example, not abelian BF theory, but for example, also quantum mechanics, several AKZ theories. If you don't know what AKZ theories are, I will introduce them in a moment. Chern-Simon theory, well, for particularly algebras, is an example of this. Two-dimensional Yang-Mills theory is also an example of this deformation. This was developed in full details by Nioff and Irazo. The Poisson sigma model is also an example of this, and so on. So there are several theories that we study, so I can skip these, or you can check in the slides. Okay, so, okay, now I want to tell you something about AKZ theories. I think maybe I can remove this stuff. Yeah, okay, good. Okay, maybe I leave the BF action above. So AKZ theories are a class of topological field theories well formulated in the BV formalism, introduced by Axelrod, Kontsevich, Schwarz, and Zaboronsky. Oh, what happens? Oh. Is it? Okay, here. So I will consider them in the so-called split case. So by split case, I assume that, so the target is a BF and V manifold. So this should be a V, not an F. So Y is our graded manifolds. Omega Y is its symplectic structure of degree n-1, and theta is a Hamiltonian function of degree n. And by split, I mean the following. Essentially, assume that omega is in the Darboux form. So omega is a differential of some one form theta, and well, this is small theta, and this theta is a sum of pi dxi. This is not the most general Darboux form in the odd case. In principle, if you have odd variables, you might have something like the odd variables times the differential of the odd variables itself. So the odd variable might be its own momentum. So that's what I know to consider now. Okay, so suppose that you have this target. To it, you can associate a field theory. So if sigma is a D-manifold, what you do is to consider essentially maps from the shifted tangent bundle of sigma to this target Y. So I will denote the supermap by capital P, capital X. So this capital P, capital X are differential forms on sigma, taking values in the coordinate P and X of the target. And then to this data, you can associate a function S, which is the integral of a sigma of this expression. So this one form gives rise to P dx. Now this D is reinterpreted as a de Rham differential on sigma. And then you take this function theta and you evaluate it in the components capital P, capital X. This will be some non-homogeneous differential form of sigma. You select the top form and you integrate it. And then you define the symplectic form by this, just sum over I delta Pi delta Xi. And again, you select the top form here. And it's an easy exercise to see that actually the BFN minus D V data are satisfied. So again, this should be a V. So namely, now this S is degree N minus D. Remember, this theta at degree N. But now we have a D-dimensional integration. So this is a degree by D. And moreover, this S Poisson commutes with itself. So this was the result of this AKZ paper. Now, you can see here that this action is actually a perturbation of a BF theory. So instead of BDA, we have PDX. Essentially, this is a abelian BF theory plus some perturbation. So these are the kind of theory that we can consider. We know how to study. Now, what is nice in this AKZ theory is that now, you see, you can take sigma of some dimension D. So we get a local BFN minus D structure. So if sigma is a boundary, we will have a BFN minus D plus 1V structure on the boundary. And it turns out that this structure on the boundary is reproduced exactly by the same AKZ construction, but applied to the boundary. So here, our general construction just, becomes more or less tautological for AKZ theories. These are automatically built in. Okay. Now we know how to do the quantization in a way that works because it's a perturbation of BF theory. So I will not enter into details here, but we know how to do it. Okay, now I think I can erase the BF theory part. Okay. Now, the interesting point here, that's the last thing I want to discuss, is, well, what happens? In abelian BF theory, you typically perturb around the zero background, but if you have some theory with this theta, non-trivial theta, you might have a lot of classical solutions. And basically the idea that you should perturb around each classical solution. So you should take this as a background. So here I will describe the simple situation where I focus on classical solutions that are constant. So we will focus on classical solution for the unperturbed part. So if you see the Euler-Lagrange equation here, say that dx should be 0 and dp should be 0. And I will focus on solution of the form p equal to 0 and x constant. Okay, so in particular, we will have some background solution, which will be some constant map from sigma to y. I will denote this constant map by small x. So this small x should also be regarded as a point in y. And the idea is to do perturbation expansion around this point. So when we do this, again, we work with affine spaces and the whole construction that I described works. The problem is to put the different expansion around different point x in connection to each other. And the nice way to do this is formal geometry that was developed by Gelfand, Krishnan, and Bott in the 70s. And I will now give you a very, very sketchy introduction to it. So suppose that Y is our target space. I will consider, suppose that I have some map phi from the tangent bundle Y to Y that I will denote this way. So for me, X will be a point on the base and Y a point on the fiber, so a tangent vector. So I will write f sub x, y for this map phi. And I assume the following. First of all, that when you restrict this to the zero section, this map phi should be the identity map. So phi x0 should be x. And moreover, I assume that this map phi should be a diffeomorphisms between the fiber and y in a neighborhood of the zero section. And actually, I normalize this a bit. So I assume that, well, the differential in the vertical direction of phi x should be the identity operator when we are on the zero section. Okay. Now, since we have these local diffeomorphisms, we can map tensor fields on y to tensor fields on the fiber of y, of ty. So namely, so if z is some tensor field, what we can do is the following. We fix some point x on the base. We take the inverse map of phi, which is defined in some neighborhood. We apply the push forward of this map to z. And so we get a tensor field on txy, on the tangent space, parameterized by x. And next, we take the Taylor expansion in the y direction. So we call this capital phi of z. Okay, so this will be some formal tensor field on the fibers of the tangent bundle, parameterized by a point on the base. Now let's do this in the case of a function. So in the case of the function, well, the push forward, the inverse is just the pullback. So we will consider the pullback of some function f. And now there is this very simple computation. Suppose that I compute, f is a function on y, on x and y. So now I can take the differential both in the x direction and in the y direction. I just use the chain rule here. And now the observation is that for y small, this matrix, I mean the differential of phi in the vertical direction is invertible. So I can compute df here by inverting dyf, and then I can insert the result here. So we see that the differential of the pullback of f in the x direction should be df, which, however, I can write as dy of the pullback composed with the dy of phi inverse, and then I still have dxf. So this is an equation that has to be satisfied by every pullback. And well, if you go locally, you easily see that these equations correspond to this equation here. There is a term which is the differential in the x direction, and there is another term here which is actually a first order operator in the vertical direction that I've written here. So these are essentially the things that I have here, right? The differential of phi in the x direction, the inverse of differential of phi in the y direction, and the differential in the y direction, this derivative here. So what we get here is now the following. We get this operator. So this R is a one form on the base, taking values in differential operator on the fiber. It turns out that this operator squares to zero. So you can think of this as a flat connection for sections of well, the complete symmetric algebra of the tangent bundle. And you see that pullback of functions are covariantly closed sections. Actually, if you work a little bit more, again, using some homotopical perturbation theory, homological perturbation theory, you can show that this is if and only if. A section is killed by this operator if and only if is the pullback of some function. So you can now regard this as a condition that selects those sections that have a global meaning. And the interesting thing is that you can extend this, the construction, to tensor fields. You can let R act on tensor fields just by the Lie derivative. And you can extend this theorem, namely a section in tensor field is killed by this connection if and only if is a push forward of the inverse of some globally defined tensor fields. So this is a, well, more abstractly, more conceptually, this procedure gives you a resolution of your manifold Y. Okay. Now, how do we apply this to field theory? Well, suppose that we start with some AKZ theory, right? So we have the PDX term and the function theta of P and X. So this P will be, I mean, some tensor field. And so what you do is the following. Now I want to work locally. So I take fields P and Q that now are maps from T1 sigma to TXY. So I fix this point X in the target. So this is a small X here, right? And I just take fields taking values in the tangent space. Now, to this theory, I can associate a theory on taking value in the tangent space, just applying this map phi to theta, right? So remember, this means just applying the push forward of the inverse of small phi, taking the Taylor expansion in the fiber. So this will be now some formal tensor field on the fiber here on TXY. So we can write down this action, and you can easily check that this action still satisfies the master equation. But what is interesting is that now you can add this other term here. So this R is this same R that appeared in this connection I wrote in the previous slide, right? And well, since it's a vector field, you can contract it with a p variable, and you can add this extra term to the action. Now this is also total, the same total degree, because well, this R is a vector field, but it's also one form on the space of on the space Y. And now you can see that this S-triddle satisfies this version of the master equation, which is called the differential master equation. So this S-triddle now is a non-homogeneous form over Y. This part is a zero form, and this part is a one form. So this equation contains a zero form part, a one form part, and the two form part. The zero form part is just the Poisson bracket of this term with itself, which is the usual master equation. The one form part says that the differential of this part, which is essentially the differential of theta, plus the Poisson bracket of this part with this part is zero. And this is just a condition that says that, well, what we have here is actually a global object. And then you can take the two form part, and the two form part is just a condition that this operator D plus R was actually a flat connection. So now all the three conditions are summarized in a single equation. Now what is nice is that you can now repeat the whole construction we did before, and you will see that when you have a boundary, that now the equation that the exponential f is to satisfy is no longer h squared delta plus omega equal to 0. Now there is this additional term, IH bar D. And of course, there are other modifications in the sense that this S is no longer a zero form. Now it would be also some non-homogeneous, it contains also one form part, what we had here. And this omega will contain also some corrections. What is interesting of this, what we call this modified differential quantum master equation, is that this gives you a clue to globalize the state. So for example, now you can take a gauge fixing, integrate, you will get a state that will be closed by the corresponding operator. And the fact that it's closed by the corresponding operator can be interpreted by saying that this state is actually the Taylor expansion of something that is global. And so you can reconstruct the global state. Okay, and now let me finish by describing this in the case of a Poisson sigma model. So this is an example of two-dimensional AKZ theory, where this function theta is just a Poisson by vector field pi. So let me switch to the usual notation for the Poisson sigma model. So instead of p and x, I will now write eta and x. And so this pi sharp is just a sharp map associated with a Poisson vector field. This is the action of the Poisson sigma model. And well, this Poisson sigma model is quite important because it's related to deformation quantization. What I proved with Giovanni several years ago is that if you take now this Poisson sigma model on a disk sigma, and you set p equal to 0, so there will be eta equal to 0 on the boundary, and then you can take the expectation values of two functions on the target evaluated on the x fields on 2 points on the boundary. It turns out that these expectation values gives you Quantized star product of the two functions f and g. Of course, in this computation, we assumed the target y to be some open domain in Rn, so that we could use coordinates, and this way we could get Quantized star product in local coordinates. The value x on which you evaluate the star product is a background you pick on the target. Now, in this computation we didn't vary the background, so the background was fixed, and as a result, we got local expression for Quantized star product. Now, Quantized, reading this paper, outlined how to globalize his local formula, actually in terms of formal geometry. We did this exercise explicitly in a paper with Giovanni Felder and Lorenzo Tomassini. So the idea is to use formal geometry as I described before. So we took this Grothendieck connection, D plus R. And the idea is that, well, Quantization provides you not only with a formula for the star product, but actually it's a so-called formality map. So here I will just skip details, but basically using this formality map, you can quantize this Grothendieck connection D to some operator D bar. So this operator D bar is by construction a derivation of the star product. The problem is that in general is not a differential. So it does not square to zero. So there will be some function f such that D bar square is a star commutator with this function f. So this function f is related to Feynman diagrams near the boundary. What is interesting is that, again, by homological perturbation theory, you can show that you can always find a one-form gamma on your manifold, taking values in formal power series of the vertical coordinates in Tm, with a property that is satisfies, oh, yeah, sorry, there should be some f here. So the property is, yeah, D bar plus 1/2 gamma star gamma should not be zero, should be f. Sorry, this should be f. So if you find a gamma with this property, and homological perturbation theory tells you that you can find such a gamma, then you can deform your operator D bar by the commutator with this gamma, and now this new operator D twiddle square to zero. So this is now the differential, and so you can go to cohomology. So we will have some associative product in the cohomology of this D twiddle, because this is a derivation as well. Right? This D bar was a derivation. This is commutator, so it's also a derivation. So you get, in cohomology, you get an associative product. And again, you can show that the cohomology in degree 0 is isomorphic to a globally defined function. So this was a way to produce a global star product. So this is how a version of the laws of construction for general Poisson manifold. And now let me finish to tell you how to implement this directly in field theory. So the idea was the following. So this is a general method, right? Applied to the Poisson sigma model. We take pi in the local formal local coordinate. We add this other term here. And well, I told you that the whole quantization construction works when you add this term. And what I was mentioning was that this construction will choose polarizations on the boundary. If you want to do deformation quantization, instead of choosing polarization, we want to fix boundary conditions. So in this case, it was fixing P or eta in the previous notation equal to 0. Now, if you do this, it turns out that things no longer work. There is some sort of anomaly term. There's a failure of the general method, but there is also an easy solution using the same gamma that appeared in the globalization procedure. So it turns out that it's enough to add to the action one extra term. So this was the action in local coordinate. This was the term depending on the Grothendieck connection. And what you can do, you can add this boundary term. So on the boundary of sigma, you integrate gamma evaluated on the field Q, right? So this is the same gamma we use for the globalization of Quantization star product. And it turns out that now things really work. So these S-twiddle satisfy the correct version of the modified differential master equation, and you can quantize. And if you now take the expectation values of function on the boundary, you really get the globalized star product. So this is somehow the way to put things together. You might think of this as some sort of one-dimensional quantum field theory that you have to add to your two-dimensional quantum field theory to make this globalization procedure work. Somehow this is a Poisson sigma model analog of factorization algebras that has to be added. Sorry for them that has to be added to Landau-Gizmo model. Okay, now let me finish to an application we had. So suppose that we do the Poisson sigma model on a surface like this. So this is actually topologically just a disk, but I split the boundary into several intervals. We have some black intervals here where we fix a Quantization boundary condition, P equal to 0. And so on these pieces, we have to add this boundary term. And then we have the blue sides. And on the blue side, we fix a polarization. And then we can quantize. So the result would be some vector in the Hilbert space, which is a product of the n+1 Hilbert spaces associated to the intervals. and this is well defined. And the idea is that here we have some sort of self-replicating structure. If I take another surfer of this kind and I glue the top interval to some of the lower interval here, and then up to diffeomorphism, I get again a surfer of this kind with more lower intervals. And it turns out that, well, since this quantization is compatible with cutting and gluing, it turns out that the composition of states satisfies some sort of associativity, of course, some sort of infinity structure. And finally, you can reconstruct a Kontsevich star product and get associativity from this previous result by considering this structure here. So this is a surfer as before with 2 lower blue interval and 1 upper one. And what you do, you glue in half disks, and on the top of this, you fix the background, and on the lower half disk, you put the 2 functions. And now you can reconstruct Kontsevich star product of f and g at the point x, just as a composition of states. So we will have a state associated with this, a state associated with this. You plug them in this state, and you will get a state associated to this disk. And when you pair it with the state that here, you will get just a new function. And this is somehow the end of my talk.
Thanks a lot, Alberto. So, so maybe we start with a question which was asked already in the end of the previous part. So this was a question of Moduli, and it is there a way to get functions on bad, I guess non-smooth or whatever, quotients as cohomology in this approach? So it relates more to the first part of your talk.
Yes, yes. Yeah, I think that this whole idea of cohomological resolution is exactly that you want to deal with bad quotients. So the point is that, yeah, I mean, bad quotient doesn't work well as a smooth manifold. The naive prescription of just taking the algebra of invariant function also doesn't work very well, because typically this algebra is very, very poor. So for example, if the quotient is not Hausdorff, this quotient algebra will only contain constant functions. So this is not good. So you have to do something else. Of course, one word is non-commutative geometry, where these quotients are generalized in terms of groupoids and sister algebras. And this way is a cohomological resolution. So you somehow define the quotient as some associated complex. And if you go to cohomology, you just get this algebra, which could be very poor. But the idea is that you don't go to cohomology. So basically, you consider a new category where your objects are complexes and morphisms are chain maps. And this is the correct category to rephrase the problem. And the interesting thing is that sometimes you can also quantize this picture. That's also the other crucial point.
Okay, good. So other questions or comments? Pavel?
Can I ask, Anton? Just a question of...
Well, yeah, Volodya, wait a second. Pavel.
Yes. Right, sorry. So there was something that I kind of missed. You said something about Landau-Ginzburg in the end. What was that about relation with Poisson model?
I mean, in Landau-Ginzburg, you have something similar, that the action is some sort of anomaly to the boundary, and you correct it by adding some one-dimensional field theory to the boundary. And this somehow
matrix optimization.
Sorry?
Could you say more? So what's the analogy?
Well, in the Landau-Ginzburg model, if you have a boundary, there is also some anomalous piece on the boundary. Well, there is related essentially to the fact that, well, it's some sort of KZ model, but there is somehow a function of degree 0 here. So a function, not by vector field. And so when you compute the master equation, this function goes to the boundary. And so this spoils the master equation. And one way to solve the problem is to add some new degrees of freedom on the boundary and some boundary theory with its own action, which compensates for this phenomenon.
So the relevant keyword there is this matrix factorization.
Matrix factorization. Sorry, not factorization. Yeah, matrix factorization. Exactly.
Aha. Okay. Okay.
Okay.
All right. Yeah.
Francis. Francis.
Yes. Yeah, I was just wondering. At the end, I saw there was something in the slides that was relating this picture of a disk with all the boundaries to a symplectic groupoid or something.
This one. This picture, or
yeah, and there was something I don't know. I saw somewhere something that was related to the
symplectic groupoid here. Yes, yes.
Can you
yes. So yeah. So well, actually, what I was describing here was a quantization of what we call the relational symplectic groupoid. So the relational symplectic groupoid is a classical picture associated to this surface. So the idea is that well, you can just take the Poisson sigma model here. Where is it? Yeah. As a classical field theory. You can compute this equation of motion. You can compute this boundary structure. There will be this reduced phase space, and somehow the Euler Lagrange equation in the bulk will define for you some Lagrangian submanifold of the reduced phase space associated to the boundary. And so this is somehow some general feature of classical field theories. And so classically, you can study what happens in this situation. So you take the Poisson sigma model in the bulk, you fix P equal to 0 on the black boundary sides, and you don't put any condition on the blue sides. Okay, so classically you will have some infinite dimensional symplectic manifold associated to the blue sides, and inside it you will have some Lagrangian submanifold induced by solutions in the bulk. And this is what we call the relational symplectic groupoid, because, well, first of all, these Lagrangian relations compose nicely. Again, if you plug in some of these objects inside another one, you can either compose these relations and get a new relations, or consider the relation on the corresponding surface, and the two things turn out to be the same. So there is these compatibility conditions. So there is some sort of associativity. And moreover, there is a quotient you can make, essentially, you see the relation with n equal to 1, so just one lower, so essentially is a strip. This actually produces some equivalence relation on this symplectic manifold. And you can go to the quotient. If the quotient is a manifold, this turns out to be the symplectic groupoid. And actually, you can push down the structure to this quotient, and this produces a symplectic groupoid on this quotient, the usual symplectic groupoid of the Poisson manifold.
Okay. Thank you. Now, Volodya, then Chen Chang.
So my question is just about terminology. When you spoke about Grothendieck connection and the formal Gelfand-Kazhdan geometry, you spoke about, but normally people speak about Grothendieck connection in the context of sheaves, I mean sheavification procedure. Do you really speak about sheaves, or you just can, for example, speak about infinite jets and flat Cartan connections and variational complex horizontal or vertical splitting? Huh?
Well, here we're actually talking of jets. So yeah, and actually, yeah, we are talking of jets, and actually, here I presented this very concrete way of producing this Grothendieck connection. Of course, there is a more conceptual way where instead of introducing this map phi, this is what is called the formal exponential map, instead you work on the infinite dimensional manifolds of coordinates on Y. This is a torsor. So there is but the associated formally group is a group of diffeomorphisms, and you have the Cartan connection there. And then you construct this Grothendieck connection essentially by choosing a section. Well, okay, so well, the point is that the only obstruction to have a section for this, for this infinite dimensional principal boundary is just GLN. So you mod out by GLN. which in my notation corresponds to choosing a formal exponential map with this property. And then you can get a section. So now you rephrase the Maurer-Cartan connection. I mean, you put back the Maurer-Cartan connection, and then you produce this connection here.
Okay, thank you. Chen-Chan?
So I have a question about this BFV. So you for example, in the case of Poisson signal model, we begin with something all about, and there's a Hamiltonian function with S, and then we do a symplectic reduction. Then we obtain the reduce the phase space, right? And then I didn't quite get then all of a sudden in this BFV theory, then you have something on the boundary, and everything reduced to the boundary. But this one was also so for example the one on Chen-Simon, BFV on Chen-Simon.
Yes.
I forgot which side was it. Validation and
here.
Yeah, over here, right? So there at a certain point I got confused. So still like so over here is still like the third point over there we denote the flat connections, and then C on the line is the quotient. Over here we're doing still the symplectic reduction, right?
Yes.
And then with the symplectic reduction, I suspect it's with this S as the Hamiltonian function, namely the moment map.
Yes,
I guess.
Yes, this is the moment map.
Yeah, that's the moment map. Yeah. Right, and then this guy, then the next line I got confused because somehow this omega underline should also come from the symplectic reduction as the general theory say, but that guy is not. It's not the symplectic reduction we did for the reduced phase space, huh?
No.
It's two different symplectic reductions.
Two different, yes. So here is the idea that you have a reduced phase space associated to a two-dimensional sigma.
Yeah.
Which is, well, the modular space of flat connections.
Right.
Okay. Now, if sigma has a boundary, there are actually two constructions. So one constructions that we typically used is to mod out by, let me see. You mod out by gauge transformations.
Right.
So that all gauge transformations, so you get a finite dimensional modular space, which, however, is no longer symplectic. This is what is typically done. This was some Poisson. There is some Poisson structure on the modular space of flat connection on the manifold with boundary, on the surface with boundary.
Without boundary, it's still symplectic, but with boundary.
Yeah, but the point, if you mod out by all gauge transformation, is not a true symplectic reduction. This is a procedure that gives you something finite dimensional, but which is only Poisson. The other approach is to mod out by actually I mean, even in the case when sigma is a boundary, there is a characteristic distribution for the space of flat connection. And this corresponds to gauge transformations that actually are trivial on the boundary. So this quotient is symplectic, but typically always is still infinite dimensional. So these are what usually other people do not consider, but this is what we consider here.
Well, that's the BFV. Okay.
That would be, yeah, the BFV. And the point is that these infinite dimensional symplectic manifold associated to a surface with boundary as projections to this Poisson manifold associated to its own boundaries.
Oh, okay. So the reference is the article you mentioned you wrote with Pavel and Veni. the reference for this thing is?
Maybe I should add that this infinite dimensional symplectic space was studied in quite detail by Meinrenken and Woodward.
Yes.
Right.
And then I think, yeah, and then I think you and Meinrenken had a way to make sense of this infinite dimensional Poisson structure and how to push it down with a finite dimensional method.
Sorry. Yeah, go ahead.
I'll answer. So this infinite thing, I remember it was to reduce the space as finite dimensional, but the mu inverse 0 is infinite dimensional in this, or did I miss something?
Can you say it again?
Yeah, could you repeat?
Okay, so the one I knew that the Eka did, maybe there's something else Eka did too, is that the mu inverse 0 in the middle is infinite dimensional, but the reduced space is still finite dimensional. No.
Only if sigma is no boundary.
Yeah, that's true.
Okay.
But sigma has no boundary, yes. But when sigma has boundary, then it's also infinite dimensional, and that was also in Eka's.
Yes.
All right. Maybe the last question for this session by Ikeda.
Thank you. Thank you very much. I would like to ask about the last part, globalization.
Mm-hmm.
D bar, operator D bar is not differential, but we can always deform.
Yes.
D bar to why? Can I ask why we can find?
Well, because it's not completely true, but well, basically, you show that there are no cohomological obstruction in the forming.
Mm-hmm.
I mean, it's non-trivial, but once you prove this, it's trivial to see it.
Is it always possible in all AK set sigma model?
No, probably not. I mean, you have to check that there are no obstructions. So in this situation, you check that the relevant cohomology is trivial.
Thank you.
Okay, thanks a lot, Alberto, for this very nice talk. And thanks a lot for the audience, for your attention and for a great number of questions. Well, I think probably it's a good point to wrap up this session of the seminar. And well, I'll send you the announcement for next week later today. Well, thank you and bye-bye.
Bye-bye.
Thank you. Bye-bye.
Bye.